This is Radhika. I am going to give a video lecture on power electronics. In this, today I am going to discuss about three-phase half-wave controlled converter with R load, and also we are going to discuss about the RL load. In previous classes, we discussed control converters and types of control converters. Today we are going to and also we discussed in previous classes half wave control converter and full wave control converter. Today we are going to discuss about advantages of three phase converters over single phase converters, connection diagram of three phase half wave control converter with R load and RL load, operation of three phase half wave controlled converter with R load and RL load, input and output waveforms for R load and RL load. Last is the derivation of average DC output voltage and R load and RL load. So, in a three phase half wave controlled converter, we have few advantages that are is the higher ripple frequency, less filtering requirements for smoothing out load current, load performance is superior as load current is mostly continuous in three phase converter. Load performance is superior as load current is mostly continuous in three phase converter. Here in three phase half wave controlled converter is the connection diagram. In this we have the three phase AC supply. Here the terminals A, B and C. Here the voltages VA, VB and VC at different terminals, and the thyristor T1, T2, T3 will be connected to three terminals, and these three are connected to load, and the load will be connected to neutral. Here at the load the output voltage is V0. The connection diagram of three phase half wave controlled converter is the diagram, and in this three phase half wave controlled converter, a three phase half wave controlled converter produces three load current pulses during one cycle of input AC three phase supply. VA, VB and VC are the instantaneous input voltages applied to T1, T2 and T3 respectively. The output is an instantaneous output voltage. The load may be resistive inductive or any DC motor load. Here a thyristor is said to be forward biased when its anode connected to highest positive instantaneous voltage. The other thyristors are said to be in reverse blocking mode. The thyristors T1, T2 and T3 will become forward biased. At omega t is equal to pi by 6 and 5 pi by 6 and 9 pi by 6 respectively. Let us suppose firing pulses applied at an angle alpha. The thyristors T1, T2 and thyristor T3 will triggered at omega t is equal to pi by 6 plus alpha and 5 pi by 6 plus alpha and 9 pi by 6 plus alpha respectively. The thyristors T1, T2, T3 will be conducted omega t is equal to pi by 6 plus alpha, 5 pi by 6 plus alpha and 9 pi by 6 plus alpha. Here this is the waveform, the conducting sequence of thyristors in three phase half wave controlled converter. So here these are three three waveforms. The red is the normal wave, and this will be leading and lagging waveforms. The red here point is 30 degrees point, and here is the 150 degrees point. It is the 270 and 390 degrees point. So here it has the pi by 3, 2 pi and 2 pi. For pi it is the half cycle, and 2 pi is the full cycle, and it has the three-phase supply conducting sequence. Here the thyristors will be conducted, first one T3, and after that the thyristor will be conducted T1, T2, T3. Again the cycle will be repeats. For each and every thyristors, the conducting period is 2 pi by 3, 2 pi by 3. In three-phase half-wave control converter with R load, the operation Wt is equal to omega t is equal to pi by 6 plus alpha. Here T1 acts as short circuit, T2, T3 acts as open circuit. The instantaneous voltage Va will be connected across R load from omega t is equal to pi by 6 to plus alpha, 2 pi by 6 plus alpha plus 120. That will be like this. Here the point A, B, C and is the neutral point. The T1, T2, T3 will be connected, and the load is resistive load. Here the output voltage is Va. The conversion when T1 will conduct, here the thyristor will be conducted. The current will flow from point A to I naught load current to resistive load, and it reverses to neutral point. At omega t pi 5 pi by 6 plus alpha, T2 is acts as closed switch, T1, T3 acts as open circuit. The instantaneous voltage Vb will be connected across R load from omega t is equal to 5 pi by 6 plus alpha to 5 pi by 6 plus alpha plus 120 degrees. Here in this diagram, at T thyristor T2 will be connected. Before diagram, the thyristor T1 will be connected. Now here the current will flow from terminal B, Vb, T2 will be conducted. The load current will flow from T2 to resistive load, and it will be returns to neutral point N. Here the output voltage will be Vb. T2 will be conduct. At three-phase half-wave control converter with R load, it is omega t is equal to 9 pi by 6 plus alpha. T3 acts as closed switch. T1, T2 acts as open circuit. The thyristor T1, T2 acts as open circuit. The instantaneous voltage Vc will be connected across R load from omega t is equal to 9 pi plus 6 plus alpha to 9 pi by 6 plus alpha plus 120 degrees. Like this, here the thyristor T3 will be connected, and T1, T2 thyristors will be in off position. The current will flow from C terminal to T3 to I naught to load the load to it returns to neutral point. Here the output voltage V0 is equal to Vc. The conversion when T3 will conduct. The waveforms are, these are the waveforms. This is the reference waveform when three-phase supply is connected. In this here continuous output voltage, the alpha is greater than 0 and less than 30 degrees. Here the output voltage will be, it has the firing angle means delay angle alpha it will be conducted at alpha and it continues up to T1, T2, T3 and the cycle will be repeats. This will be conducted at pi by 6 plus alpha and 5 pi by 6 plus alpha and 9 pi by 6 plus alpha. So here this is the output voltage at alpha is equal to 30 degrees, and this is the last one is the output voltage when discontinuous output voltage, that will be alpha is the less than 30 and greater than 30 and less than 150. The input and output waveforms of three-phase half-wave controlled converter with R load. Here the three-phase half-wave controlled converter with R load, average output voltage V0 is equal to area under the curve over considered cycle by time period for the same cycle, that is 1 by periodic time integral of Va d omega t. Here this is the three-phase half-wave control converter with R load is the, in case of case 1, if V0 is continuous, the alpha is greater than 0 and less than 30 degrees. So here the output voltage V0 is equal to 1 by 2 pi by 3 of pi by 6 plus alpha integral of, here V0 is equal to 1 by 2 pi by 3 integral of pi by 6 plus alpha to 5 pi by 6 plus alpha Va d omega t. Here that is 3 by 2 pi integral of pi by 6 plus alpha to 5 pi by 6 alpha Vmp sin omega t d omega t. After calculation of this one, we will get 3 Vmp by 2 pi of minus cos omega t of pi by 6 plus alpha to 5 pi by 6 plus alpha. After substitution of these values, we will get 3 under root of 3 Vmp by 2 pi cos alpha. Here Vmp is the maximum value of phase voltage V phase. In case of case B, V0 is discontinuous, means the alpha is greater than 30, less than 150 from the waveform, that is the output voltage is 1 by 2 pi by 3 integral of pi by 6 plus alpha to pi Va d omega t, that will be 3 by 2 pi integral of pi by 6 plus alpha to pi by 6 Vmp sin omega t d omega t. Here that will be 3 Vmp by 2 pi of minus cos omega t of pi by 6 plus alpha to pi. After substitution of these integrals, we will get output voltage is equal to 3 Vmp by 2 pi into 1 plus cos pi by 6 plus alpha. So in three-phase half-wave control converter with R load. So before going to this one,
half-wave controlled rectifier is shown here. The circuit consists of a delta star transformer and 3 thyristors T1, T2, T3, which are connected on the secondary star connected winding and a resistive load. In this circuit, three-phase power supply is available to the converter through three-phase transformer with a delta connected primary and star connected secondary. VA, VB, VC are the phase voltages. I0 is the output current or load current and V0 is the output or load voltage. When VA is positive, the thyristor T1 becomes forward biased and conducts. During the negative half cycle of VA, the thyristor T1 turns off. Similarly, T2 and T3 conducts only during the positive cycles of VB and VC respectively. So consider the three-phase supply voltage. From 0 to 30, two voltages are there, VC and VA. And we can see that VA is less than compared to VC. So, if we are giving firing pulses to T1 from 0 to 30, the thyristor T1 does not conduct because VA is less than compared to VC. But from 30 to 150 degree, from here to here, we can see that VA is greater than VB and VC. So, if we are giving firing pulses during this interval, that is from 30 to 150 degree to T1, then T1 conducts. Again, from 150 degree to 270 degree, we can see that magnitude of VB is higher than VA and VC. Therefore, from 150 to 270 degree, if we are giving firing pulses to T2, T2 becomes turned on. Similarly, from 270 to 390 degree, the magnitude of VC is higher than VA and VB. So, if we are giving firing pulses during this interval, then only thyristor T3 turned on. So, we can say that the thyristor T1 conducts during the interval 30 to 150 degree, 30 to 150 degree, and thyristor T2 conducts during the interval 150 to 270 degree, 150 to 270 degree, and the thyristor T3 conducts during the interval 270 to 390 degree. T3 during the interval 270 to 390 degree and so on. So, in case of three-phase rectifier, this point, that is omega t is equal to 30 degree is the zero firing angle for T1. So, this point is the alpha is equal to 0 for thyristor T1. Similarly, this point, omega t is equal to 150 degree is the firing angle 0 point of the thyristor T2. And this point, omega t is equal to 270 is the 0 firing angle point of T3. Again, this point is the 0, alpha is equal to 0 for T1 and so on. And also we can see that the three thyristors T1, T2 and T3 are triggered by firing pulses at regular intervals of 120 degree in each cycle. From 60 to 150, 120 degree interval. From 150 to 270, 120 degree interval and 270 to 390 120 degree interval. So next we will draw the load voltage V0 with different firing angles. So consider alpha is equal to 0 degree. We already discussed that alpha is equal to 0 for T1 means omega t is equal to 30 degree and T2 omega t is equal to 150 degree and alpha is equal to 0 for T3 means omega t is equal to 270 degree. So these are the 0 firing angle points of T1, T2, T3 respectively. So when alpha is equal to 0 degree, firing pulse is given to T1 at omega t is equal to 30 degree. So here in this point, firing pulse is given to T1 and firing pulses are given to T2 at omega t is equal to 150 degree and firing pulses are given to T3 at omega t is equal to 270 degree. So first consider at omega t is equal to 30 degree, firing pulse is given to T1. So this voltage VA appearing across the load. So this voltage VA appearing across the load. So this one is VA. And the thyristor T1 continues to conduct until the next thyristor T2 is turned on. So here at omega t is equal to 150 degree, firing pulses are given to T2. Therefore, T2 is turned on and the load current I0 transferred from T1 to T2. So load current flows through this path. So the voltage VB appearing across the load. So from omega t is equal to 150 degree, this voltage appearing across the load. So the voltage, this voltage. Voltage VB appearing across the load. And here also the thyristor T2 continues to conduct until the next thyristor T3 is fired. At omega t is equal to 270 degree, here firing pulses are given to T3. So the T3 is turned on and the load current I0 transfers from T2 to T3. So the current flows through this path. So this voltage appearing across the load, VC voltage appearing across the load. So this one is VC. Again at omega t is equal to 390 degree, firing pulses are given to T1. So T1 is turned on and the load current transferred from T3 to T1. So this voltage VA appearing across the load. So here in this portion VC is higher compared to VA and VB. Therefore thyristor T3 is in the on state and this voltage VC appearing across the load. So this one is VC appearing across the load. So this one is the output voltage waveform at firing angle alpha is equal to 0 degree. Next we will discuss the condition when firing angle alpha less than 30 degree. Means alpha can take any values between 0 and 30 degree. 0 less than equal to alpha less than or equal to 30 degree. So this one is the alpha is equal to 0 for T1 and this interval is 30 degree. So alpha can be anywhere between 30 and 60. So for T1 we can give firing pulses in between 30 and 60. So here we are giving firing pulses to T1 and this one is the alpha is equal to 0 for T2, that is 150 degree. So in second case we can give firing pulses to T2 anywhere between 150 and 180 degree. So we can give firing pulses here. Similarly in T3 we can give firing pulses here. Again for T1 we can give firing pulses here. When omega t is equal to 30 plus alpha. So this one is alpha, 30 plus alpha. Firing pulses are given to T1. At omega t is equal to 150 plus alpha, firing pulses are given to T2. Therefore, from 30 plus alpha to 150 plus alpha, T1 is in the on state. 30 plus alpha to 150 plus alpha, thyristor T1 is in the on state. So the voltage VA appearing across the load. So you can see this blue colored waveform. So this waveform appearing across the load from here to here. So this one is 30 plus alpha and this point is 150 plus alpha. So 30 plus alpha to 150 plus alpha, this waveform appearing across the load. So up to this point. At omega t is equal to 150 plus alpha, this point firing pulses are given to T2 and omega t is equal to 270 plus alpha, firing pulses are given to T3. So from 150 plus alpha to 270 plus alpha, thyristor T2 is in the on state. So this waveform from here to here, red colored sinusoidal waveform, this waveform appears across the load. So this voltage, appears across the load. So here T1 conducts, here T2 conducts. Similarly from 270 plus alpha to 390 plus alpha, T3 is in the on state. So this voltage VC appears across the load. So this voltage, this one is here T3 conducts. Again from 390 plus alpha, thyristor T1 conducts. Again thyristor T1 conducts. So here thyristor T3 is in the on state because VC is greater than VA and VB. Consider the next condition, alpha greater than 30 degree. So this point is alpha is equal to 0 degree and this 60 means alpha is equal to 30 degree. So we can give firing pulses anywhere after 60 degree. So here I am giving firing pulses between 60 and 90 degree. So here I am giving firing pulses to T1. Similarly, here giving firing pulses to T2. Here giving firing pulses to T3. again firing pulses are given to T1. So consider the first case. So this one is alpha is equal to 0 point, that is omega t is equal to 30. So we can say that this point is 30 plus alpha, where alpha is greater than 30 degree. From this point, that is omega t is equal to 30 plus alpha, firing pulses are given to thyristor T1. So thyristor starts conducting from this point. So this waveform appearing across the load. Here you can see that at 180 degree, that is this point. So this point is 30 plus alpha. At omega t is equal to 180 degree, VA is 0. After that, negative voltage appearing across the thyristor T1. So at this point, natural commutation of thyristor T1 takes place and thyristor T1 is in the off state. So from here to 180 degree, thyristor T1 conducts and this voltage appears across the load. So from 180 to 150 plus alpha. So this point is 150 plus alpha. T1, T is equal to 180 degree. VA is 0. After that, negative voltage appearing across the thyristor T1. So at this point, natural commutation of thyristor T1 takes place and thyristor T1 is in the off state. So from here to 180 degree, thyristor T1 conducts and this voltage appears across the load. So from 180 to 150 plus alpha. So this point is 150 plus alpha. T1, T2, T3 are in the off state. At omega t is equal to 150 plus alpha, this point, firing pulse is given to thyristor T2. So T2 starts conducting from 150 plus alpha to 300. So this voltage appearing across the load from 150 plus alpha to 300. Again at omega t is equal to 270 plus alpha, this point, firing pulses are given to T3. So from 270 plus alpha, this point to 420, thyristor T3 is in the on state and so this voltage appears across the load. So this point is 270 plus alpha and this one is 420. So from 270 plus alpha to 420, thyristor T3 conducts and also during this interval 0 to 60 degree, T3 conducts. T3 conducts. Thank you.
So we watched a YouTube lecture about the um, three-phase half-wave controlled converter with resistive load. And also now we have here this the three-phase half-wave controlled converter with the RL load. In this also the difference is only the here load. The load will be series connected with the R, but the remaining conduction is same, but the waveforms is different. Here using of inductive load we have the only below x-axis, only that is the due to inductance, only that is the difference between R and RL load. And here Same. In summary, the conducting sequence of thyristors in three-phase half-wave control converter is 5 by pi by 6 plus alpha, 5 pi by 6 plus alpha and 9 pi by 6 plus alpha respectively. Each thyristor will conduct one at a time for 120 degrees. The average DC output voltage V0 of a three-phase half-wave control converter decreases as the firing angle alpha increases. The expressions for average DC output voltage V0 are: for R load, V0 is equal to 3 under root of 3 Vmp by 2 pi cos alpha for continuous wave, and output voltage 3 Vmp by 2 pi of 1 plus cos pi by 6 plus alpha for discontinuous. Is RL load, for RL load, output voltage V0 is equal to 3 root 3 Vmp by 2 pi cos alpha for continuous waveform. So here we have the few quiz questions and few frequently asked questions. So this is the today's class, three-phase half-wave control converter with resistive load. Thank you.